take a few minutes to go through the answer key. I think for the most part it's self-explanatory, but sometimes it's helpful to talk about things that are clear. The first couple of questions were supposed to be giveaways. That is to say, questions that would make you stop and think for a moment or two, but would get you rolling, get some momentum going, so that when you came to the harder questions later, you'd be rolling along well enough. So the first one is a typical probability question from deck of cards kind of problem, and of course, I guess, I discovered that there were one or two people who didn't know what a deck of cards looked like, and then didn't notice that I had put it up on the blackboard. But in any case, there are 52 cards in a deck. There are 4 suits. Half the cards are red and half the cards are black, divided along the suits, so that hearts and diamonds are red, spades and clubs are black cards. There are 3 face cards in every suit, Jack, Queen, King. And there are 4 aces, which we removed from the deck because depending on the card game, aces are either played high or low. And so rather than have that confusion in the question, we took the aces out. So I'm sure that certainly the people who grew up in a Western country, when you played hearts and Old Maid and bridge and things like that in college, depending on the particular group that you were playing with, aces were high or aces were low, depending on what you were trying to do in the card game. Yeah, so we took those problematic ones out, and leaving the cards 2 through king left in each suit for a total of 48 cards. So in this card game, you would get $1 for drawing a red card, of which there are 24. You would get $2 for drawing a club, of which there are only 12 left. You would get $7 for a spade, number 2 through 9, and there are 8 of those. And you would win $10 for the 10 Jack, Queen, King of spades, of which there are 4. And those groupings are mutually exclusive and collectively exhaustive. There's no intersection between those groupings. That would be an interesting problem to allow that kind of intersection, but that would take a little bit too much time. It's not really, doesn't add that much to the question. So a probability distribution for the payoff would look like that. In the first column, I listed the dollar payoffs. In the second column, I listed the probabilities with which those payoffs would occur. And you can look at that and you can see that all the probabilities are between 0 and 1, and they add to 1. So they define a proper probability distribution. In computing the mean of the random variable x, which is the draw of a card, is the weighted sum of the possible payoffs, where the weights are the probabilities with which they occur. So I put together the answer key in MathCAD, and one of the quirks in MathCAD is that, which once you've used MathCAD for a while and you understand everything that it does, you begin to appreciate the fact that it's not really a quirk. But they begin the indexing for matrices and vectors with 0. So the first column of the matrix is the 0th column, and the next column over is the first, and so on and so forth. So if you have, still leave it at that. So that's why it says, for example, multiply the ith row, the element in the ith row, the 0th column of dist, by the ith row and the first column of dist. So the first column was that column of probabilities, and the 0th column had the payoffs in. And so the mean turned out to be 3. And doing the variance the same way, the variance of the random variable x is the squared deviations around its mean weighted by the probabilities of occurrence. These are just simple definitions, either from your introductory statistics course that you took, whenever you took it, or straight out of the lecture notes. And that variance turned out to be 9. The second question said, show that x1 plus x2 is an unbiased estimator of the rate parameter in a Poisson process. And I think, I wasn't going to do it, but I figured since there had been a question about formula sheets prior to the exam, I figured, well, I'll throw a formula in there just to keep everybody's momentum going. So a de minimis answer would be to argue that the expected value of a Poisson random variable is equal to lambda. And that's common knowledge. A few people took the time and effort to derive that result, which was great. I really enjoyed seeing that some people, not only did they know the fact, but they also knew how to derive it. And that also is something that's in the lecture notes. And while I didn't explicitly stop and write it on the board, it's there. So if you argue that the expected value of a Poisson random variable is equal to lambda, the rate parameter, you're done, essentially. Because then you're looking at the expected value of x1, which is Poisson, plus the expected value of x2, which is a Poisson random variable drawn from a distribution with the same rate parameter, and you're averaging lambda plus lambda. And you're done. So that's kind of the de minimis answer. You only had to write 3 sentences, and you would have gotten all the points. Although it was really gratifying, as I said, to see that some people took the time to stop and demonstrate the first result, which is that the expected value of the Poisson random variable is equal to the rate parameter. It's a fairly simple thing to do. It's because, as we know, the expected value of any random variable, any discrete random variable, is the sum of the xi f of xi. And in this case, it was the sum from I, and now this is over the 0 to, this is over the support of the random variable. So it's the sum of the xi, e to the minus lambda to the xi over xi factorial. So this becomes similar to a change of the limits of integration in a change of variable problem. In integration, calculus, you do things like change the variable of integration, and then you have to change the limits of integration correspondingly. So one of the things that you can do is cancel, let's take you can cancel an x, so we end up with the sum from 0 to infinity of e to the minus lambda to the x, x minus 1 factorial. And so the next step is to factor out a lambda. So we have the sum from 0 to infinity of e to the minus lambda to the x minus 1 over x minus 1 factorial. So now do the change of variable. And the change of variable is then to look at the sum from 1 to infinity of e to the minus lambda to the y over y factorial. And we know that sums to 1 because the Poisson is a probability distribution, and you just end up with lambda. So it's a quick little 3-line derivation. But you didn't need to get the whole point, so you didn't need to do that. You just had to say, this is something we know about the Poisson probability distribution. The expected value of the Poisson random variable is equal to the rate parameter. And we got 2 of them, and we're dividing by 2. So we're done. And that, by the way, is in your lecture notes.